right, why don't we get started? Thanks so much for joining me. My name is Dean Wampler. I work for Anyscale, and this is a talk about Ray, which is the open source project that Anyscale was started to develop. Ray was actually developed initially at the University of California at Berkeley. I'll explain kind of why it was developed and what we hope to accomplish with it. I do welcome feedback at Anyscale.com, on Twitter, Dean Wampler. And if you want to learn more about Ray or Anyscale, you can check out those links. We have some events of our own this summer, webinar kind of events, and also I'm teaching tutorials on reinforcement learning and other topics that you can find out about at Anyscale.com/events. And we post information about past events at our blog site. Okay, so what I'm going to do is kind of explain why we need Ray by discussing kind of the challenges of distributed computing, especially if they've been made extreme by machine learning and AI. So sort of the inspiration for Ray and how that problem set led to the creation of Ray. I'll give you a sense of the Ray API and why I think it's such a good API in terms of being very easy to use, intuitive for people who need to scale mostly Python applications across a cluster for getting the benefits of distributed computing without having to know a whole lot about distributed computing theory and so forth. But mostly I'll also talk about the reinforcement learning library and other AI libraries that are built on top of Ray. Those are the things you might use most if you're doing data science kind of work. You may not even deal with Ray itself, but it's behind the scenes doing a lot of the work for you. And then I'll finish with a little bit about how you could start using Ray if you're interested. All right, so let's sort of make the case for why Ray is a really useful tool for this problem. And I'm going to pitch this in the sense of basically deploying machine learning and AI as a microservice. There's a lot of reasons why you might build microservices. I don't want to go into all of them. I just want to focus on this last one, which is a common sort of really the DevOps part of the talk. That often we need to deploy things separately for a bunch of different reasons. Like, for example, we might need to spin up different instances or different numbers of instances because of the load that they're carrying. Let's suppose microservice 3 here is a model serving library, and maybe it's evolving quickly, so we need to roll out new versions frequently while keeping the API the same. Let's say microservice 1 doesn't change as often, but it needs a lot more instances because of the load it's carrying. I mean, these are sort of standard reasons why we have to do this. But it really kind of sucks that we have to manage these things ourselves explicitly. We have to do that because we run into the boundaries of single nodes, what they can hold. So we need to go across a cluster for distribution just to scale. But also we like to do this for resiliency, so if a node goes down, we don't lose work. Well, kind of the beauty of Ray, as we'll kind of examine a little bit more detail in a moment, is that it gives you the ability to think back on an abstraction of just having one instance, your main application driver, if you will. And then behind the scenes, Ray can scale the work across a cluster to give you both the resiliency and the quote unquote infinite scalability that you might want. So it greatly simplifies the problem of managing microservices and kind of takes away even the name in a sense. Now, I don't want to oversell this. It doesn't solve all problems. You have to be willing to accept, say, the 80% solution that Ray provides in terms of how things are managed. If you need tighter control, then you might have to go to something that's a little bit more explicit about how things are managed. But for a lot of the problems that we've run into, especially in this world of data science, it's really quite sufficient for what most people need. And it works nicely with systems like Kubernetes, whether you're running on bare metal or containers, pods, virtual machines, and a cloud provider. All of those things, it just nests nicely because Ray is working at a fine-grained level of abstraction, much finer than, say, the sort of pod level or machine level abstractions. Okay, so what I tried to do there is to give you a sense of how Ray takes away a lot of the pain of day-to-day management of highly scalable, highly resilient services. So let's look at the API a little bit to get a sense of why that's so. And I'm going to start actually by giving you the motivation for Ray. And it really kind of answers two major trends. One is from this rather famous blog post from OpenAI that the compute required to train models has been growing like a factor of 35 every 18 months or so. That's a log scale on the left. That roughly correlates to model size, for example. Whereas, Moore's law and sort of a corollary idea called Dennard scaling, you get roughly 2x performance every 18 months or so. So obviously, Moore's law, even with GPUs, isn't keeping up with the compute demands. So it's just making it more and more necessary to go distributed. The other big trend that kind of drives Ray is the fact that Python has seen enormous growth in the last decade or so, largely driven by data science and related workloads. But Python itself is not a terribly good language for distributed computing. And most Python developers, especially in the data science space, don't really want to have to deal with distributed computing technology per se. So they really need something that's robust, but really easy to use to distribute Python applications. Now I'm going to stick with Python for the rest. It turns out Ray is actually flexible enough for other languages, and we even have an early version of a Java API, but mostly we're targeting Python developers right now. So if you kind of look at just a typical landscape of all the work people do in machine learning, and this is just one way of representing that, a bunch of different tasks that we have to do, everything from featureizing, ETLing our systems to stream processing as a corollary to that, hyperparameter tuning, training, simulation, et cetera. There's a whole lot of tools that have been developed for these particular problems, some of which overlap, as you can see with the icons. But kind of the idea with Ray was, there's a lot of commonality here in terms of distributed computing. Can we actually build something that could be the underpinnings of all of these things? So the view of Ray, the vision of Ray is that we have this framework that can underlie all of these things. And on top of it, you would have domain-specific libraries for hyperparameter tuning, training, reinforcement learning, model serving. These are the four that we have right now. And there's other third-party projects that are using Ray, like Spacey for natural language processing, as an example. So just very quickly, what's it like to work with Ray? Again, if you're a data scientist, you might not actually use this very often because you'll be working at a higher level. But just to give you a sense of what it's doing for you, imagine I have these two Python functions. And it sort of fits the model of what we tried to do with Ray, which is let's take concepts people already understand, like putting work in a function, and figure out how to make that, extend that to be distributed without a lot of mental load to be bared. So this is Python you already know. I'm just two fake functions, one of which will construct a NumPy array, and then another one which will add two arrays together. And if I add this decorator, this annotation, this adornment, I get ray.remote, and that turns these functions into tasks, which means that Ray will be able to distribute these over a cluster, or over all the CPU cores in a single machine, which isn't trivial to do in Python by itself. Now, for completeness, there's some import statements you have to add, and you have to initialize Ray in your code. So what actually happens is when you call these tasks, you actually use a remote function, and that's going to return an ID for a future. This is like a handle for the work that will be completed eventually, and you'll be able to get the value that was computed from that handle. I can call it twice, I get two handles, and then I could pass the two handles to add arrays. Now, there's a couple of magic things going on here. Well, first, the first thing I need to do is to call ray.get when I'm finally finished to get the value I want. But what I didn't have to do was carefully watch to see what was finished and then sequence the calls. Ray managed the dependencies between these tasks automatically. And the other thing it did is I didn't have to stop and grab the arrays from the first two calls and then stuff them into add arrays. Ray could do that for me. So it does a lot of work for you. It sort of looks like regular synchronous programming. The remote method is good to know when you see that because it tells you that Ray is involved rather than trying to guess what's actually going on. But it otherwise feels like normal synchronous programming. Now, what this doesn't do so far is handle distributed state. It kind of assumes these are stateless functions that I'm operating with. Once again, leverage a familiar idea, which is classes from Python. Here I have a very simple class called a counter. Every time I call increment, it's going to increment this counter. And so it's holding state for me. And this could be arbitrarily big, complicated state, but I think you get the idea. Familiar idea, wrap it in a class. And then once again, add this decorator, ray.remote, that turns it into an actor. Now the term actor is a historical term. I won't go into details about what it means, but you can just think of this as a distributed autonomous agent that can manage its state updates in a thread-safe way and so forth. One other thing I had to add, I need a getter method. Actors don't let you just reach in and read the values. You have to use a method to get the values. Excuse me. So call it the same way. We use the remote method. And I kind of went too fast, but you can then call ray.get to get the values out. All right, so that's the core idea. What was going on behind the scenes was I was writing code that kind of looked like regular Python code, but it was actually being distributed over a cluster, and the dependencies between tasks and actor method calls was being coordinated by Ray, so I don't have to worry about all that stuff. So let's talk a little bit about the libraries built on top of Ray. We saw this before where I showed 4 libraries at the top. I'm only going to talk about one today, which is the reinforcement learning library. This was really the first thing that was built with Ray, because as we'll see, reinforcement learning kind of really drove the need for something like Ray. If you're not familiar with reinforcement learning, here's a 30-second crash course. Basically, you have some agent that's observing an environment. It takes actions or makes decisions in that environment and then observes what kind of rewards, for some definition of reward, it receives. And the goal is to train this agent to maximize its rewards over a long period of time. So it's a very different kind of machine learning model. It got really popular a few years ago, about 5 years ago, when it was used to beat the world's best Go player, to play Atari games and other things. Previously, it was kind of an obscure part of machine learning. And it's also been used for training autonomous vehicles and robotics, simulators like the thing at the bottom. And we're starting to see new applications like improving industrial processes. I picked this example of modern assembly line. Excuse me, my throat's scratchy today. Optimizing things like heating and cooling systems, power, network topologies, network communications. There's some well-known examples of using it to improve advertising and recommendations, like at YouTube and Netflix. In fact, I think this diagram is from a Netflix paper, if I recall correctly. And as always, anything new, they try to do better at finance, trading with such a thing. And trading is kind of a nice fit because it's also something that's going to, proceed in kind of a time sequential way. And you'd like to be able to navigate through the world of the market, if you will, in a good way. And I somehow turn this on. Okay. So the architecture of RLlib is basically trying to support all of these things in a very flexible way. This top level means that it integrates with some popular libraries like OpenAI Gym, which is a simulator for various kind of problem domains. You might have more than one agent interacting with the environment. And then you might be doing things like serving policy that's already been trained, or actually training on log data because you can't run a simulator. Maybe you can't simulate your chemical factory very well, but you have really good log data, telemetry from past execution that you can train against. That sits on top of either custom algorithms you write or other people have written and contributed to Ray, as well as the ones we built in. A lot of the popular ones are already implemented for you. And then there's a, boy, sorry about my throat today. And there's a bunch of composable abstractions that we use to give you, the reinforcement learning. And all of that is then running on top of Ray to give you distributed execution over a cluster, mostly transparently. And there's some knobs you can tune, like I need GPUs for this and so forth, but a lot of it is just done automatically for you. You can actually use Ray inside SageMaker if you want on Amazon. And Azure has recently rolled out support for reinforcement learning using Ray and RLlib. One of the interesting things about reinforcement learning that kind of drove Ray in general was the fact that there's just a diverse range of compute and memory access patterns used. These simulators, these game engines, they look a lot more like regular apps and not very much like traditional, big data, data flow, SQL query kind of problems. So they need special compute. We want all this to be efficient, right? Because we're going to be running a lot of these things to train this stuff in parallel over a cluster. You might be serving policy as well as training it. There are situations where you're training as you serve, on the fly, online learning, so to speak. And then all these different topologies between the actors, the agents, the environment, and so forth. So all of that kind of diverse compute is what drove that very simple, low-level, concise API that I showed you earlier. But once you have something like that, then it's broadly applicable, not only for reinforcement learning, but for hyperparameter tuning, one of the other libraries that I mentioned, but we won't go into, model serving, training, and also microservices. So Ray was really born with this problem in mind, be as flexible as needed for this diverse range of compute. But it's got to be efficient, right? So Ray does perform very well against some other implementations of some of the standard algorithms like proximal policy optimization, deep queue networks, and so forth. So finally, what if you want to adopt Ray? What are some things you might want to know? Well, it turns out if you're already writing code that uses these popular libraries like joblib and multiprocessing.pool, you can just drop in Ray replacements, usually by just replacing import statements. And they pretty much work the same way, except now they break through the single node limitation and let you scale to a cluster. So that's kind of nice. We've also implemented Ray with the async IO. So if you like using that coroutine model, that works nicely too. In fact, it's an alternative to the API I showed you before. If you're more interested in Ray, check out ray.io. I'm developing tutorials, and I'm actually teaching a tutorial next week on reinforcement learning if you're interested. And you can find the Git repo at this link here, the Academy link. And we like to help people that need help. So the Ray Slack is a good place to go. And then there's a Ray Dev Google group. So to conclude, Ray is this new state-of-the-art system for distributed computing. It's designed to minimize the effort it takes to go from like prototyping your Python application on a laptop to running in a distributed way on a cloud or whatever topology you have. And it's designed for quite a range of diverse, complex compute tasks like you encounter in various machine learning problems. Okay, so I think I might have finished just a bit early, but I'm happy to take questions. We do have that chat feature for you to ask questions. Before I switch over to that, once again, here are the links, ray.io, anyscale.com. We are hiring if you're interested. You can reach out to me at dean@anyscale.com or on Twitter at deanwampler. And do check out these events we have this summer, like the training I mentioned for next week. And we post a lot of stuff in our blog as well. Okay, so let me stop sharing my screen and go back to the window, and I can answer some of these questions. All right. Okay, so really good question. Someone asked, how does Ray compare to Dask? This is a pretty common question. And here's the way I like to answer this. If you are doing distributed pandas or distributed NumPy arrays, very much oriented towards kind of what you might be using Spark for example, then Dask is a really good choice because it's really focused on that problem domain very well. If you need general distributed computation, we think Ray is much more flexible, much more robust, and much more performant. And so we're kind of focused more on enabling these complex compute problems in reinforcement learning and so forth. So that's the trade-off I would make. I would decide which problem do you need solved first, and then pick the tool that fits best. And for things like pandas and so forth, Dask is really good for that. Someone asked, can I use Ray in a non-ML application, simply as an actor-based application like Kaka or Erlang? So I used to work for Lightband, very familiar with Kaka. And the answer is yes. I try to give you the sense of that a little bit by showing you the API and also showing you this idea that it simplifies microservices. Actually, our biggest user of Ray turns out to be a financial firm in China that mostly isn't using Ray for machine learning. They're using it for very, very large scale services like fraud detection and session management and stuff like that. So it's very nice for that. The difference I think you'd find between Ray and say Erlang and Kaka is that I think Ray is easier to get started with. The API, there isn't much more than what I showed you. There are some ways you can dive in a little bit deeper, but it really kind of goes with the model of being as simple as possible and then making really good default choices about what to do behind the scenes with some ability to configure that. Whereas Erlang and Kaka tend to be more on the other side, more developer oriented towards, I'm going to give you every possible thing you could want, give you all the power that you could possibly need, but you will have to step up a little bit more to be most effective using it. So that's sort of my thinking about it. That's one of the things that attracted me about Ray actually coming from the Kaka world, is that I did find that it's, because it's really focused on people who don't want to think about distributed computing, who just need it and want it to be as easy to get to as possible and are willing to live with a lot of default behaviors. I think they did a really good job sort of aiming at that user space. Someone asked too, what about using sklearn random forests and pandas, for example? Yeah, actually, so it turns out the JobLib support that I mentioned is really aimed at supporting sklearn. There is, let's see, there's, actually, I'll make the slides available. I think we're going to upload slides. I actually don't really know for sure for the conference, but you could always reach out to me, dean@anyscale.com, for the slides if you can't find them anywhere else. But they do have some links in there to blog posts. Or I'll tell you what, you could also just Google like the Ray blog, and you'll find blog posts that talk about using scikit-learn and our replacement for JobLib, and see how that fits your problem. Hopefully you'll find that it has the right flexibility for what you're trying to do. Someone asked, what am I going to cover in the tutorial? It is intended to be an intro tutorial next week. It's both covering how to use RLlib and what is reinforcement learning. So if you're already an expert, then you might find the first bits a little boring, or maybe a good review, whatever you decide. But I just welcome you to check it out and see if you like it. You can actually go to github.com/anyscale/academy and find all this material. I will tell you that the reinforcement learning material is kind of beta quality at the moment. There's some fine tuning that we're doing before next week. That's the purpose of next week's tutorial. And I actually did a live tutorial a month ago on the core of Ray. If you go to the Anyscale blog, you can find the link to the video for that, and that code is also in the same repo. So Anyscale Academy on GitHub. Okay. What other questions? Can Ray be married with GPU compute to accelerate computations? Yes. I probably should have left this slide in. I took it out because I thought I'd run out of time. But when you do those ray.remote things, you can actually say this function needs 2 GPUs or whatever. You can actually specify resources there. And you can also do it globally. Like when you initialize Ray, I mentioned briefly that you call this ray.init. You can actually say things like, I need 300 CPU cores and I need 20 GPUs or whatever. So it does integrate nicely. Mostly what it's doing in these cases is leveraging the underlying, like when you're doing this with RLlib, for example, it's leveraging the hooks inside PyTorch or TensorFlow or whatever to do that. But it does understand these kind of resources. Is it available in GCP? Interesting question, because I don't think it's actually integrated with any of GPU services in the same way I mentioned for Azure and SageMaker. We are working on making it much easier to just spin up Ray clusters on GCP. There's some early work being done there. As you can imagine, we kind of tended to test most with AWS initially, but when you're spinning up stuff yourself, it's actually a very simple model for spinning up clusters, so it's pretty easy to do it. We're just trying to make sure that it's much easier, even as easy as possible, let's say, and there's no gotchas when you do it on GCP. We're almost there. So how would companies use Ray in production, say on AWS on SageMaker, for example? Yeah, so you would basically, if you ever did, well, I don't know, if you ever did Spark, where you just spun up your own hand-rolled cluster, you basically start a head node with Ray. It's a very similar model, in other words. And then you spin up Ray on the other nodes, and it does a lot of the synchronization and sort of federation itself behind the scenes once you do that. So there is a process of bootstrapping. It's pretty straightforward. We're also working on making that robust because there's a little bit of single point of failure issues right now with that head node, as you can imagine. But it is actually quite simple to start it up. It's not a heavyweight thing. It's not like starting up a Hadoop cluster per se, but you basically start these processes that run as daemons on each node, and they talk to each other to manage distribution of work. There are a few other things running in the background you might notice. I'll just mention them so you're not confused. It is actually using Redis for some of the distributed object management. And it does actually use the Plasma library from pandas if you see that kind of stuff floating around in your cluster. Let's see. What about node scaling up and down on requirements? There is actually an autoscaler feature. I'm actually just learning about it myself, so I don't know all of the capabilities yet. It's been developed with some systems like Kubernetes in mind and AWS, but it is actually very agnostic about what you're doing. So you should check that out. And if you have any questions about it, you can reach out to me. And another place you can reach out to is academy@anyscale.com. I respond to those emails as well. But let me know if you have any questions about the autoscaler. But that's what you want to look at in the documentation, is the autoscaler. How about comparing RLlib versus Coach? I honestly don't know much about Coach, so I certainly not enough to badmouth it or anything. So but not even to compare it in a good way. So I just don't know enough about it to provide a good comparison. The things I would look at though to evaluate them are, in either case, are the performance characteristics what you want? Are the APIs what you need? Is the ease of use what you like? Does it integrate well with whatever infrastructure or other APIs and stuff you want to use? Yeah, we think it's pretty good, but if you think otherwise, I'd love to hear that too. We always want to know how we can make it better. This is an interesting question, I think. What about IoT? Can Ray run on constrained devices? It's actually fairly lightweight. It's not as lightweight as it could be. Someone asked about Akka earlier. Akka was really famous for keeping actor overhead down to hundreds of bytes. It was basically sharing resources to the point where any one actor really only needed a few hundred bytes and then some shared infrastructure. Ray is a little bit more coarse-grained. It's like tens of megabytes per actor right now. And then part of that is because it's also running like Python code. There's a C++ kernel in the middle and all this kind of stuff. So depending on how constrained the device is, you could certainly do it. I think what you would want to be careful about, though, is I don't think you'd want to build a network topology where you're relying on actors and the distributed devices communicating back to the mothership. I don't think, just to, in full disclosure, I doubt we've tested that kind of flaky network scenario as well as we could have, and certainly dynamic network topologies and stuff. So I would be careful about doing that, like a distributed Ray topology. But if you wanted to use Ray to maximize the use of cores in an ARM processor, then that might actually work really well, especially if you're already planning to use Python. I'd love to hear about that story, actually. So once again, if what works or doesn't work, reach out to us. We'd love to hear stories like that and see how we can help make it better if it's needed. Besides large data workflows and managing the JVM, how does Ray compare to PySpark? Yeah, really good question. What I think and Spark in general, its main strengths, and I used to use Spark a lot in previous lives. What I love about it is it gives you really powerful composable abstractions for like sequences of data. And I'm thinking more like, streaming data or reading data at rest, but you want to process it in mass, do massive joins, group bys, and stuff like that. And then actually use real SQL to do this in some cases. So for any of those kind of scenarios, Spark can't be beat. And I think we don't have anything like that. We've really focused on this problem of like distributed object graphs in the old object-oriented sense because of the general compute requirements of things like machine learning. You can load big data sets in memory if you want, but it's not managed in sort of the automatic way, especially with partitioning the way that Spark does. So I actually think they're very complementary. If you hate using or having to deploy the JVM, then that might push you more towards something like Ray or Dask even for pandas. But otherwise, I think they actually complement each other a little bit more than contrast. I'm actually doing a talk at Spark Summit next week, and I'm showing how to embed some Ray code as a UDF in a Spark SQL job. To be honest, it's a bit of a hack, but it does kind of illustrate this sort of complementarity that's possible, which was my goal there. Anybody have any others? I think TensorFlow integrates with Spark. Does that make sense with Ray? Yes, it does, actually. Both RLlib and Tune will use TensorFlow on, as you want them to. Just with one slight caveat. In RLlibs, there are a few algorithms that haven't been ported between PyTorch and TensorFlow and vice versa. But for the most part, we try to be Switzerland, if you will, neutral about using really good systems like TensorFlow, PyTorch, scikit-learn, and so forth. So they do integrate very nicely. So just to kind of peel the onion just a little bit, like suppose you wanted to do a hyperparameter tuning of a neural network with TensorFlow, you basically declare, use TensorFlow, use this algorithm for training, blah, 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 and run. And Ray would kind of manage the coordination behind the scenes, but it would be using these big libraries to do all the heavy lifting. Anything else anybody has? I appreciate the good questions. These are great. Can I not use, let's see, pandas data from inside the hit node? Okay, so question, just to paraphrase the question, what about if I have pandas, a big pandas data frame, can I compute over the partitions? You actually could do this. I haven't tried this myself, but here's what you ought to do. Look, there is one research project called Modin, M-O-D-I-N. It's a team at Berkeley that is actually integrating Ray with the pandas API. And you might see what they're doing. I don't think it's quite ready for production, that system, but it does illustrate how you could integrate the two together to kind of do that compute over partitions. But beyond that, I don't really know what details I would recommend for you. Anything else? How are we doing for time? I'm happy to, oh, is Ray free? Yes, it is. It's all open source. We are building some services that would make it easier to run Ray in cloud environments, but it's basically all open source stuff. Like most companies, we realize that that's the future. So it has to be open or no one will actually even try it to begin with. Are there limitations on the Python interface? Can you pass higher order functions to the methods? Yes, you can actually. So what Ray does is it pickles all of the dependencies and stuff that's needed for that task to send it off. So you can actually do this. To be honest, I don't know that I've actually done it myself, just to verify that. But yeah, it should work. I've certainly seen examples doing this. Obviously, to be safe, you'd probably want to use something that doesn't close over a lot of state, but maybe if it's a stateless little function, like a sorting or a comparator or something like that, then that should work fine. Okay, probably running out of questions. Once again, I'd love to hear your feedback. Dean at Anyscale.com, and I'll make the slides available to the conference, and you can also get them from me that way if you need to. Thanks for the feedback. Appreciate it. And thanks for tuning in again. And I hope you enjoy using Ray. All right. Thanks a lot, and enjoy the rest of the conference.